We are continuing in this example. I had stopped and saw a mistake, and I fixed it, and we'll continue from here. In the notes, you may have seen I had a 5 here on accident. So when you solve this, this should be a 1, and that ends up being a 5, and it, of course, messed everything up. So I wanted to redo it, but not have to redo everything. So here we go. So here's our system we want to show is linearly dependent, although I didn't say that right off the bat, but it's pretty clear it is because you have rows zeroing out. But let's go kind of all the way and show that you can find a non-trivial solution to the system. So we're here. This is the stuff we've done before. I just wanted to make sure we go through it again. This one's, I don't think we did one this complicated in the past, so here we go. So from here, I set up this system, solving the homogeneous case like you do, and row reduced using a calculator to here. And now you can see, here's your diagonal. You see you have actually 3 free variables, R3, R4, R5. And then we'll solve for the rest. So that's what we'll have. Show what we have. So I'd write out from here. I would just say R1 plus 3R2 minus 4R3 plus 2R4. And then I can say 0R5 if I want, equal to 0. And then we have 4R2 plus 3R3 plus R5 equal to 0, which is 1. That's the mistake I made. And then we have R4 minus R5 equal to 0. And this, well, yeah, that was a 0. So R4 equals R5, but we also have R4 and R5 can be anything. So there can be anything, but they're the same. So we have 0R4 is 0, and 0R5 is 0. So we basically have here, I guess I put this in here. So I have 0R3 is equal to 0. So R4 and R5, and really because of this, we don't really need that R4 equals R5 because they can be anything for the solution. So R4 and R3, all of these are arbitrary, can be whatever. So R3 we'll say is T and R, oops. I forgot to make those equal signs. Let's do this right. R, okay, so that's an R. Okay, then this would be S, and this I picked C. I'm going to choose them to be a value though. So I'm going to let R3 equal R4 equal R5 all be 1. You don't really want them to be 0 because the whole point is showing that you can find a solution that they're not all 0. So let's make them something else. And then we just go back and solve for R1 and R2. So we get R1 plus 3R2 minus 4 plus 2 equal to 0. Solving for R1, R1 is equal to negative 3R2 plus 2. And I have that 4R2 plus 3 plus 1 equal to 0. So 4R2 is equal to negative 4. So R2 is equal to negative 1. So if R2 is negative 1, that implies that R1 is equal to negative 3 times negative 1 plus 2 is equal to 5. And so I end up with a non-trivial solution for that system. Therefore, the vectors are linearly dependent. So 5, negative 1, and then 1, 1, 1. It is a non-trivial solution. Therefore, I think I called it U, right? Yeah, U is linearly dependent. Okay, so remember, what makes it independent is if the only way to get 0, right, which is what you're doing here, the only way to get 0, well, actually it's here. The only way to get 0 is if every single one of these are 0. And that didn't happen. We found a solution that by this process that is non-zero. Okay, so if you put those values, you may want to check this. If you put those values back in here and add it up, you should get 0. And so basically, we can check it real quick, can't we? That'd be really easy, actually. Well, I wouldn't say really easy. Easy for us, maybe. So those are all 1s. And so you get, here's your x, I'm going to erase this stuff, but here's your x squared, that's gone, right? And then what else? And then you have your x values. So x, 3x, and 4x. And then, oh, I almost forgot 5. So R, oh, and then one of them is negative. Oh, there you go. This one's negative, right? I should have just gone through it, huh? That's negative. And then this is 5. And so when you add that up, here's your, I'll just point. Okay, so this is 5. That's negative. So those are gone. And then we have, this is 5, and then it should have a negative 5. So here's 3. Well, that's a negative 3. Negative 2, and yep, that's it. Because this is negative 1, so negative 3. And negative 2, because of this, gives us negative 5, because of this. Add 5 and you get 0. So it worked. Anyway, sorry if that messed you up. Check that and see if it makes sense to you. Okay. Next one, let's look at this example. These are linearly independent functions. This is number 14. So show that sine x, cosine x is linearly independent. So it's get kind of weird how to show this because you have like, it has to be true for every case and all this. So what we want to do is here's your f, here's your g. So the whole goal is to show r sine x, I'll just say r and s is fine, and then s cosine x equal to 0. So I keep saying the only way to get that is 0. Well, that's kind of true, but for functions, what you're trying to show is that we want to find a case where the only solution to the system is 0, 0. So if you can do that, then there's no way to make a combination of the two, so they're always 0. So what you do, there's a couple ways of doing this. You can take derivatives of whatever's here, and that's one of the techniques you can check out in the book. Or we can pick values and show that you have cases that you get both R and S to be 0. So what we do, and what they show you, is we're going to choose first X to be 0, and then X to be pi halves, because it's sine and cosine. So by doing that, you get R plus, or times 0 plus S equal to 0. And then if you solve that, you get S is equal to 0. It's an if and only if, actually. And then similarly, you get R plus S times 0, if and only if R is equal to 0. So we found a case where the only solution to the system is 0, 0. Okay, so therefore linearly independent. But think about it too. I mean, there's no way to make a combination. There's no trig identities. Think of trig identities that make sine into cosine. They're completely different. You can't combine the two. It's like saying sine, e to the x and sine x. You can't get one into the other by doing addition and scalar multiples. Okay, so look at a couple of those. I wouldn't worry a whole lot about all these procedures, but just you'll be able to do it. Not a big deal. Okay, next we'll get on to basis and a couple theorems and a proof. And then that'll be it for 3.2. Then we'll go on to 3.3.